Okay, this is lesson 4 of module 5. We're going to see more examples of functions, and we're going to experience a way of classifying types of functions. So we're going to first look at some examples we've already seen. So table A represents a function, and it represents a proportional relationship too. So the the price of a bag of candy is the same, or the cost of a bag of candy is the same, no matter how many bags you buy. So if you buy 8 bags, it's still $1.25 per bag. So we worked on that one in lesson 3. It's a constant rate problem. That is a linear function because a linear equation describes it, or is the rule for it. Table B is motion. So we've got the number of seconds that an object is traveling and the distance that it has traveled in feet. So we can see that in the first half second, the object has traveled 4 feet. If we look here from half a second to the time that the object has been traveling 1 second, now we've gone 12. Okay, so we can already see this is not linear. The increase from 1 to 1.5, that's another half second, but now it's increasing by 20. So you can see that this object is actually speeding up. So it's probably a falling object and speeding up because of the force due to gravity. Another thing about these two functions that are represented by these tables is that there's constraints on the inputs. So for table A, we talked about this when we looked at this problem in the last lesson. We can only have integer values for bags of candy. In fact, we can only have non-negative integers. Okay, so we can have 0. We could have 0, 1, 2, 3, 4, 5, 6, 7, 8. And we can keep going. We could have 9, 10, 11, 12. But we can't have 1.5 or 2.5 or 1 1/10 or anything except an integer, because we're assuming that the bags have to be sold together. Okay, so those are the kind of constraints on the inputs and outputs for that function. For this function, we've got x already being a non-integer, a decimal number here. It's and we could have a lot more inputs than this. We could have 6/10 of a second. We could have 1 75/100ths. So for this one, we could go in between these numbers and beyond these numbers. Well, not beyond, because this one only went up to 4. So, but this one definitely has a constraint that the input has to be positive. But within this range of values, it could be any decimal or fractional representation of a second. The outputs are also going to be positive because the distance traveled is going to be positive. Okay, and you might remember that this function that is represented in table B had a rule of y is equal to 16x squared. Okay, and we know that that's not going to graph as a line because of the power of 2 on the variable here. So we saw that for it to be a line, it would have to have an exponent of 1 or 0. Okay, so we've talked about the constraints on the inputs and outputs for both of these functions, but there's something going on that is different between these two, that besides the fact that they have different inputs. So let's look at some definitions here. So we can classify these functions, and so there's such a thing as a discrete function. So the word discrete has a definition, and it means individually separate or unique. So discrete functions are functions that only allow separate input values. And so those are said to be discrete. And so the example of that would be our sale of the bags of candy, because we can only buy them in whole number increments. Okay, but a lot of functions are not discrete. Often these are called continuous functions, but for now we're just going to call them not discrete. And they're functions that can take all input values over a given range. And motion is an example of that. If we've got time, we can have fractions of a second and have an output for that input. So go ahead and pause the video and look at example 1. And you've got A through I, quite a few problems there. And you can take a look at those and try to classify each of these functions as discrete or not discrete. So what you're looking at is you're looking at the input to tell if a function is discrete or not discrete. If it's continuous over a range, then it is not discrete. If the inputs are separate, it is discrete. Okay, we'll quickly go through the responses here. So let's look at A. All we're doing is saying whether these inputs are discrete or not discrete. So we have a function that assigns to each whole number the cost of buying that many cans of beans in a particular grocery store. So the input would be the number of cans of beans, and we can only have those in integer increments. So this function is discrete. Part B, the function that assigns to each time of day, one Wednesday, the temperature of Sammy's fever at that time. That's not a well punctuated sentence, but that would be not discrete, because we could take Sammy's temperature at any time over that interval. So that is not discrete. Those are continuous inputs. Okay, the function that assigns to each real number its digit, its first digit. Okay, so real numbers are not discrete. They are continuous. We can always find another decimal in between. So this would not be a discrete function. All right, so D. The function that assigns to each day in the year 2015 my height at noon that day. All right, so because we're looking at individual days and not continuous time, that's going to be a discrete function. Okay, part E. The function that assigns to each moment in the year 2015 my height at that moment. So the word moment is our key there. If we're talking about moments, those are not discrete, because I could pick any given moment and they're continuous. The moments are continuous. Okay, part F. The function that assigns to each color the first letter of the name of that color. Okay, so colors are discrete or separate inputs, and so this is a discrete function. Okay, so let's look at the last three now. Okay, if you're having trouble with these, don't worry about it. It might take a little bit of a few more examples before you really get the hang of it. But you can certainly call and ask a question. Okay, so part G, the function that assigns the number 23 to each and every real number between 20 and 30.6. Okay, so our inputs are the real numbers between 20 and 30.6. And within that range, the real numbers are continuous. So this is not a discrete function right here, not discrete. So even though every output is the same, it's 23, it's still a function because every input has a unique output, but all the outputs are the same. Okay, not a very interesting function there. All right, so let's look at H, the function that assigns the word yes to every yes/no question. So the inputs are the yes/no questions, and those are separate items or separate inputs, and so that is a discrete function. Okay, last one, the function that assigns to each height directly above the North Pole the temperature of the air at that height, right at this very moment. Okay, so if you think about the heights above the North Pole, that would be a continuous interval of measurements. And so this would be not a discrete function because we could choose any height within a range. Okay, so example 2 is another problem that we're revisiting. This is the one where water's flowing from a faucet into a bathtub at a constant rate of 7 gallons every 2 minutes. It says regard the volume of the water accumulated in the tub as a function of the number of minutes the faucet has been on. Okay, so the amount of water in the tub depends on the number of minutes the faucet has been on. Is this function discrete or not discrete? So remember this, the rate was 3.5 gallons per minute. And so our function was y is equal to 3.5 times x. And so that's our function. So if you think about what inputs could we have for this, my input is going to be time, so it's going to be the amount of time in minutes, but I could have fractional values here. Obviously can't be less than 0, but any number in a reasonable range would work. So this would be not a discrete function. It's not discrete because we're dealing with a time interval that we could go down to fractions of a second if we wanted to. So this function is not discrete. Okay, example 3 is a bit more complicated of an example of a non-discrete function. So let's look at it. You have just been served freshly made soup that is so hot it cannot be eaten. The soup is 210 degrees, and so that's almost boiling. There's no way that it could safely be eaten yet. 1 minute after receiving the soup, the temperature has dropped to 203 degrees. If you assume that the rate at which the soup cools is constant, write an equation that would describe the temperature of the soup over time. Okay, so let's just kind of step through this. So the soup is 210 degrees to start with, and we know that after 1 minute, it's decreased to 203 degrees. So that is a decrease of 7 degrees in temperature over 1 minute. So if I continue at this rate, then after another minute, I'm going to drop another 7 degrees down to 196. Okay, so this is a constant rate problem. I can write a linear equation that would model this. So if you think about it, the temperature starts out at 210 degrees. So I could say that y, which I'm using to stand for the temperature, is 210 degrees. And then it has every minute another 7 is subtracted off. So if I multiply 7 times the number of minutes that the soup is cooling and subtract that from 210, then I would have the temperature of the soup at any time x. Okay, so if we assume that 147 degrees is a safe temperature at which to eat the soup, then I could put that in for y here. So I'm substituting 147 in for the temperature, and so I get 147 is equal to this expression here. And I can solve for x by subtracting 210 from both sides, then dividing by -7, and I get that x is equal to 9. And so remember we said x is the number of minutes, so what that means is that after, not 9 seconds, but after 9 minutes, the soup is 147 degrees. Okay, so let's continue with example 3. So we wrote a linear model, y equals 210 minus 7x, where y is the temperature of the soup at any time, and x is the amount of time that the soup has been cooling. So that was what we decided to use as a model because based on what happened during the first minute. But we can see here this table is measurements of temperature that were taken every minute as the soup cooled. So after 2 minutes, remember we had 210 minus 7 times 2 minus 14, which is equal to 196. So this table of actual temperatures matches the after 2 minutes, but notice what happens in the next minute. It only drops 6 degrees here, not another full 7. So what happens then is that after 9 minutes, where we said it would be 147 degrees, the soup is still 158. So it's not cooling off as fast as our linear model thought that it would. So since our rate is not constant, the decrease in temperature is not happening at a constant rate, this is actually going to be a nonlinear function. And the particular nonlinear function that it is given by this. So if y is the temperature, then this would be 70 plus 140 times this fraction, 133 over 140 to the power of x. So this is a nonlinear function that would model the actual cooling of the soup. Okay, so this is not following the rules for what we see as linear because the variable is actually the exponent. So it's kind of an interesting function, not one that you'll be dealing with for the next couple years in math, but at some point in high school math and physics, you'll see equations like this. Okay, our final example, example 4, is a little bit different. So this is a function that assigns to each of 9 baseball players who are numbered 1 through 9 their height. So the data for this function is given below. So player number 1 has a height of 5 feet 11, and player 2 is 5 foot 4 inches, and so on. We're going to call this function g. So you can see if the input is player 3, then the output is 5 foot 9 inches. Okay, so if we're going to call this a function because whenever I put in the player number, there's only one height. My height doesn't change. And so if I'm player 3 and my height is 5'9", that this function's always going to assign that height to this player. Okay, now, are there any players that have the same height? So let's look down the data table. Okay, so here's another 5'9". 5'9". So player 3 is 5'9", player 7 is 5'9", but this is still a function because there's a unique output for every input. Some of them are used more than once, but that's okay. It still makes it a good predictor for player, the height of a player given its number. So is this a discrete function or a not discrete function? So hopefully you could see that this would be a discrete function because our inputs are separate. They're all individual players, so this would be a discrete function. But if we try to find a formula for this particular function here, function g, we're going to have a hard time. There is no formula that says if a player's number is, 5, then this is how you calculate the height. Okay, so this is a function, but it's a function that doesn't have a formula. Okay, now you have exercises 1 through 3 in your classwork, and you can work on those independently and come back and check your answers with the video. Okay, so for exercise 1, the situation is we need buses to transport students. Each bus can hold up to 35 students, and B is going to be a function that assigns to the input, which will be the count of the number of students. It's going to assign the number of buses needed to transport that many students on a field trip. Okay, so when Jinpo thought about the problem, he created the following table showing the number of buses needed for 35, 70, 105, and 140 students. And he wrote an equation which looks like this, that B is equal to X divided by 35, where X is the count of students and B is the number of buses needed. And he said this is a linear function. Okay, so he certainly made it look linear. This looks like a constant increase right here. But Alicia looked at his work, and even though his arithmetic was correct, she said the function was not linear. And she is right. Part A tells us she's right, but why is she right? Why is this not a linear function? Well, if you think about the number of students and the number of buses, he has not written all of the inputs here. So what about 36 students? So if I hit 36 students, I'm going to need a second bus, and so I would need 2 buses there. Same for 37, and so on. I could write a lot more inputs other than these increments of 35 here. So there's all these inputs here, and if you think about it, this is not a constant rate of increase. So I go along with 1 bus for a long time up to 35, and then all of a sudden at 36 I need 2 buses, and I go along that way all the way up to 71 when I need 3 buses. So it's kind of stepping up, and it's not doing it gradually. So we could say that the rate of increase of buses is not constant. Okay, so it's not a consistent rate of increase. So it's not a linear function, but it is a function. Even though I have the same output for several numbers of students, I still have a unique output for every input, and that's the definition of a function. That makes it a good predictor, okay? I can use this to predict the number of buses, but it's not linear, okay? So is this a discrete function? It is. It's discrete because the inputs, which is number of students, are integers. I can't have a fractional part of a student, so I can only, they're separate entities, and so that makes this a discrete function. Okay, example 2. In example 2, we're told is a linear function. So that means something special. It means we've got a constant rate of increase. And so I can assume this relationship, that it's going to be a proportional relationship even in this circumstance. So I have X being the number of tickets that are bought and Y being the total cost. So if I want to find the unit rate, I can take any of those input-output pairs and divide to find that it's $9.25 per ticket. So even if I took 111 divided by 12, or $83.25 and divided by 9, would always get $9.25 per ticket. It's a constant rate of increase because it's a linear function. Okay, so I've got this unit rate, so I can write an equation. We can write a linear equation that models this linear function. So if Y is the cost and X is the number of tickets, you could see that Y, the cost, is going to be equal to $9.25 times the number of tickets that are purchased. All right, so part B says, is the function discrete? Yes, it's a discrete function. And once again, it's discrete because the inputs are integers. I can't buy half a ticket, so I can buy 3 or 4 or 5, but those would be separate. So that's the meaning of discrete, that the inputs are separate. What number does the function assign to 4? And what is that? What is the question that's being asked, and what does the answer mean there? So first of all, what number does the function, and here's our function rule right here, what number does it assign to 4? Well, that means I'm going to put in 4 for the input, and I would get Y is equal to 9.25 times 4, and Y is equal to 37. And so the question and answer is, another way of saying that is, what is the cost for 4 tickets? So the cost for 4 tickets is $37. Okay, the input is number of tickets, the output is the total cost. Okay, example 3 is a good way to end this lesson. So here we have a function relationship that is not mathematical at all. Okay, so we have a function and it produces the following inputs and outputs. So if I input banana, I output B. If I input cat, I output C, and so on. So make a guess as to the rule this function follows. Each input has to be a word from the English language. And so hopefully you guess that what this function does is it takes the first letter of the word and that becomes the output. So you can see I could put in the word, I could put ball in and my output would be B again. But it's still a function because each input is going to have a single output, a unique output. Okay, so if you guess that rule, that is the rule. And is this function discrete? So this is a discrete function because the inputs are separate items. There's not a continuous nature to the inputs. They're just words in the English language. So it could be any word in the English language could be an input here. So that makes this a discrete function. Okay, so in this lesson we learned that we can classify functions as discrete or not discrete. And we saw that discrete functions have inputs that are separate values, such as whole numbers of students or words or tickets or things like that. Functions that are not discrete admit any input value over a range of values. So you could have fractions, you could have decimals, and so on. Functions that describe motion were generally the ones that were not discrete. The other functions were discrete. The other thing we did in this lesson is just get more practice with writing rules for linear functions and noticing by looking at tables of values and situations and that whether a function was going to be linear or not. Okay, so good luck with the exit ticket and the problem set. You're ready to go.